All right, so this is lesson 7 from the unit. So this is the 5th lesson after March break. So it's listed as number 5 for the week of April 6th, April 10th. I don't have any graphing paper with me, so this one's going to be a little tricky. Maybe to interpret some of the graphs because I'm doing them on just the regular line paper. But I don't think it should be that big of a problem. I'll be careful. So we'll start up. Just pull up the lesson. So the first thing we're going to refresh is inverse functions. So we're going to look at the function y equals x plus 2. Is this showing up? Yes, perfect. Y equals x plus 2. Sorry, not x plus 2, x squared plus 2. We'll make a table of values based on that. So if we put x equals negative 2 in, negative 2 squared is 4, plus 2 is 6, negative 1 squared is 1, plus 2 is 3, 0 squared is 0, plus 2 is 2, 1 squared is 1, plus 2 is 3, 2 squared plus 2 gives us 6. We have these 5 points. Negative 2, 6, negative 1, 3, 0, 2, 1, 3, and 2, 6. And if we're going to look at the inverse function, that means inverse, we're switching our x and our y's. So before we had negative 2, 6, now we're going to have 6, negative 2, 3, negative 1, 2, 0, 3, 1, 6, 2. And we're going to plot this and see what does this look like. That should be good. We'll plot our original function. So negative 2, 6, 2, 4, 6. It's going to be right here. Negative 1, 3, 0, 2, 1, 3, and 2, 6. Again, not perfect, but hopefully good enough to give you the shape. We get a parabola opening up, vertex is right at 0, 2. And our inverse function I'll do in pencil. Yes, I should check. Can you see this? Barely. Let's move it down. So if we do this in pencil, 6, negative 2, another point out here, 6, negative 2, be down here, 3, negative 1, 2, 0, 1, 3, 3, 1, 6, 2. We get a parabola, or a parabola-like shape, opening to the right. Like this. And if you remember from last year, you would have talked about, let's switch back to the pen, that an inverse function is really like we're reflecting across the line y equals x. So this function gets flipped across this line, and we get an inverse. The parabola, each point is reflected directly across the line. Again, the graphs on the completed notes online will do a much better job of showing that than my rough drawings. So you can check that there if you want another look. But every single inverse is always a reflection over this line y equals x. If we want to look algebraically, we look at our original function, y equals x squared plus 2. And we're going to switch our x's and our y's. So wherever there's a y, it becomes an x. Wherever there's an x, it becomes a y. So that's going to give us x equals y squared plus 2. So that's what we're doing when we're switching the x's and y's in the table of values. And then, because we're used to giving our functions as a function of y, we're going to solve for y. So we'll move over the positive 2 to the left side, and we get x minus 2 equals y squared. And then we'll take the square root plus or minus square root of both sides, and we get y equals plus or minus the square root of x minus 2. So if our original function was f of x is x squared plus 2, if we were to write the inverse, we'll say f inverse is plus or minus the square root of x minus 2. So this, again, was our symbol for inverse of x, just in case we forgot. That's kind of a refresh on inverses. Now we're going to look at inverses of exponential functions. So you would have talked about exponential functions last year. We're going to look to start at the function f of x equals 2 to the power of x. So one of the more basic exponential functions, one of the ones you normally start with when you were first talking about exponential functions last year. And we'll look at the table of values just to refresh. Let me just pencil here so I know when I'm going to run out of space and you can't see it on the video anymore. 2 to the power of 0, anything to the power of 0 is going to give us 1. 2 to the power of 1 is 2. 2 to the power of 2 is 4. 2 to the power of 3 is 8. And we're multiplying by 2 each time. We're dividing by 2 each time we go up. 2 to the negative 1 is a half. Negative 2, we get a quarter. And 2 to the negative 3, we get an eighth. So we get 3, negative 3, 1 over 8. Negative 2, 1 over 4. Negative 1, 1 half. 0, 1, 1, 2, 2, 4, 3, 8. So now our inverse function we're going to get negative 1 over 8. Sorry, 1 over 8, negative 3. We're switching all of our x and y values. Now if we go to graph this, need a little more space. So if we graph this, we'll graph the original function first. So negative 3, 1 over 8, negative 2 and a quarter, negative 1.5, 0 and 1, 1 and 2, 2 and 4, 3 and 8. We can see that exponential shape. I'm sure you've been hearing a lot about exponentials in the last 2 months or so. And now our inverse, 1 over 8, negative 3, quarter, negative 2, 1/2, negative 1, 1, 0, 2, 1, 4, 2, 8, 3, and this is our inverse function, which inverse of 2 to the power of x is going to be log base 2 of x. So on the blank note, there's a spot to talk about key features. So our original f of x equals 2 to the power of x. We have a y intercept. I realize now this is way far off. Y-intercept of 0, 1, whereas there's no y-intercept in the inverse. X-intercept in the original, there was none. And now in the inverse, it's at 1, 0. So you can see these kind of alternate. Domain of the original is all real numbers. Range of the original, we have to be greater than 0. Domain of our inverse, x was always greater than 0. But our range could be all real numbers. Asymptote, in the original function we had a horizontal asymptote at y equals 0. In the inverse we had a vertical asymptote at x equals 0. And then our original, we were always increasing, always going up when we look left to right. and our inverse is always increasing. So if you remember looking back at our rational functions, we talked about if the original function's increasing, the new function's also increasing. Same thing goes here. Let's see. Algebraically, I'll turn the page here. In order to get that log, prove that log 2 base 2 of x is our inverse. I should probably spell algebraically right. So original function, y equals 2x, x. So we're looking at f of x equals 2 to the power of x. We switch our x and y. X equals 2 to the power of y. Then we need to solve for y. So we need to turn this into logarithmic form. So log base of our exponent is 2, base of our log is 2. Oh, getting ahead of myself. This x is going to become our argument, and that's going to equal the exponent in exponential form. And so that right there, that y equals log base 2x, that's our inverse. And finally to ask, use the graph to find or estimate. So we're using y log base 2x to estimate x equals 8. If we look back at the graph, our logarithmic function x equals 8, y was equal to 3. We actually got that right from our table of values as well. Y equals log base 2 of 8. Y equals 3. So our point is 8, 3. B, we're doing the exact same thing, but for x equals 6. Let's go back. 1, 2, 3, 4, 5, 6. Somewhere up here. A little less than 3 in the notes in a little bit better graph. It looks more like 2.6. This looks like it could be log base 2 of 6. It looks like maybe 2.8, 2.9. We'll say 2.8. On the calculator, in order to calculate log base 2 of 6, we need to do log 6 divided by log 2. And that will give us 2.58, about 2.6. So again, that graph, not log, 2.6. So again, that graph in the notes is better than this rough sketch that I've done. Let's look at, so we looked at a growth equation. Let's look at a decay equation. So we'll look at f of x equals 1/2 to the power of x. So we'll do the same points. Look from -3 to 3. 1/2 to the -3 is 8. 1/2 to the -2 is 4. 2 to to the power of 0 is 1. 1/2 to the 1 is 1/2. 1/2 squared. 1/4 to the power of 3 equals 1/8. So we have this list of points. And for the inverse, we get all those points again reversed. So -2, 4 becomes 4, -2, and so on. One, 8, 3. So I don't have quite enough room to go by ones. So let's go by twos.